So, what's the best reflectivity for a laser diode? The answer is that depends on your target output power. Why? Let's consider the mirror with a low reflectivity. A low reflectivity means a high mirror loss. When the mirror loss is high, that means your model gain is also high. In order to achieve a high model gain, you need to inject more carrier to achieve population inversion. That means your threshold current density will be higher. However, if your reflectivity is pretty high, almost 1, in such case, then surely your threshold current density will be much smaller. But since all the photons are confined within your cavity, only a small portion of them will be measured by you. So the differential efficiency will be lower than the one with a low reflectivity. So let's consider two cases. The blue one with a high reflectivity at both sides. A red one with a low reflectivity at both sides. While you want to do a low power application, probably you only need 1 milliwatt or few hundreds of microwatt. Which one give you a lower threshold operation current? The blue one. However, if your required power is high, for example, you need a 1 watt laser to hit people, or a 1 watt blue laser will burn the mesh. If you shine it on the top of the mesh, it will make the light the mesh burn. Okay, so you will highlight that although the threshold is high, but most of the photon after lasing will be acquired by you. So in this case, actually a poorer mirror give you a lower operation current. So it is a value need to be optimized. So this is also a homework of you. So you can see the operation current will be your threshold current times, since you have the slope, you know the slope here. So it will be the power divided by slope. So it will be the second injecting current after that. So that will be ITH will be this term, and then the second term will be P0Q divided by zeta D divided by H mu. So that was second current. So this one means since this is the water and in the beginning is a constant. So if I give you a reference, you can know what's the threshold current density after changing the mirror loss. But with the different mirror loss, that will give you also a different slope here. That will calculate the exact current necessary to achieve a specific output power. Then you can try to plot the I versus R, point by point by point. Then you can abstract a minimum value for your application. Then that will be your optimal design for your semiconductor laser. So it is not the lower is bad or higher is bad. That really depends on your final purpose. And this also confirms the previous statement that the low threshold design and high power design are usually incomplete with each other. So in the last section we talked about the IV curve, PI curve under a steady state. But for a laser or while we are doing communication, it's a dynamic process. we need to turn the laser on as the signal 1 and turn the laser off of the signal 0. This is the Li curve we have under steady state. That means you turn the current slightly, slowly, and measure your power also under a macroscopic scale, probably in milliseconds or microseconds. Even microseconds is pretty low for laser because the interaction between electron and the photon is always in the level of nanosecond and picosecond. So microsecond is already a pretty long time. Alright, but now consider we are doing the current with a sinusoidal way. That means we have a central the current called I0 and modulate that simultaneously with the amplitude I1 and times the exponential term for the meaning of oscillation. Alright. Since it is under the it is after lasing, so the NTH, N should be at NTH. Let me draw this again. So under steady state, it should be in the NTH. And we said that if your current, so this is I, make a sudden change like this, then the NTH will increase first, then oscillating back and forth, and then eventually return to the NTH. This is the gain trapping phenomenon. However, what happens if you suddenly turn the back off and turns on again? Okay, so this is how you operate your laser now. So the carrier might turn on at the beginning, but after it reaches your equilibrium, it's turned off. Then it goes on again. So under this case, the modulation might be forced due to a non-steady current input. So so let me change the color. So with a pulse like this, the final result might be also oscillating with your carrier also because you didn't give him enough time to return its steady state. Alright. So while you have a current modulation with a frequency of omega, in the rate equation, it means this one is time dependent. That makes the carrier density also a modulating term. It will be NTH plus amplitude with oscillating term. And the change of the carrier density via the term of the stimulated emission also modulate the photon density inside your cavity. So you have also a baseline value with the amplitude MP1 and the oscillating term. And the such oscillating term also influence the carrier density. Okay, due to the stimulated emission, since it is coupled. Then part of them leaving the cavity become the measurable output power. So that also makes the output power escalating like this. So you also have the P1 and the oscillating exponential j omega t. Okay. So now we do things like this. First, we make the G to be GTH because it is a clamped at steady state with a dG over dN times dN. So this is a total differential. dg over Tn times delta n. And what's dg over Dn? dg over Dn is defined as the slope of your gain curve near lacing. So A will be dg over Dn. For a two-carrier model, a two-parameter model, in the empirical model, we write that g of n is the ln g0 ln n over n ti. dg over dn is g0 times n ti over n. In the exponent, so it's in the numerator with n over n ti. Okay, that would be better writing now. N over n ti over 1. And further, you have the n t over 1 for the chain rule. So it is n over g0. And this is also the definition of differential equation. So you can replace this one into your rate. Or for simply put, we can just use the letter n, letter a, since you might use a free parameter model or something. So let's keep it original sign. Let's replace the dg over Tn as the small letter a. And the delta n is the n1 exponential I omega t. This is the modulating term. Okay, so plug in this into the g here. So this original g becomes gth plus an1 exponential I omega t. Similarly, for the photon ray equation like this, then it's a series of mathematical operation. Purely algebraic and tedious, so I'm gonna skip that. But I will tell you how to do that. First, you also plug in I is equal to the I0, I1 exponential, n as well, np as well. And the second, because we know that for those terms with th or 0 in the subscription belongs to the steady state term. So you can remove all of them because dg over dt is equal to 0 under steady state. So you will reduce a lot of them at the second state. Third, some of them will have the exponential I omega t tied together, so generate exponential I2 omega t. Those terms will be treated as the noise of the background. And you will directly negate that. Pretend it doesn't exist. Yeah, that's sounds a little bit convenient, but that's okay. Reasonable for real engineering purpose. Then replace the GTH term with the gamma Vg tau p, the one you have in the equation. Okay. Then after such three operations, you can see the exponential I omega t will be the common term at both sides. Then you can remove that. Okay, so the rate equation for current modulation turns to the term 210 here. I omega n1 will be tau I I1 QVA . And this is the rate equation of the photon. Then we'll subsequently do the mistake operation. Since we have the equation like this, we can let n1 to be the I omega n1 divided by gamma Vg ANP0, and put the whole term inside the here. And we know that the P1 is using the same definition. But remember, this is the subscription 1, so this is the dynamic term. with O1 here, and then finally plug in NP1 by this equation into 1 as well. Then finally it becomes a pretty complicated case, like P1 in the function of omega divided by I1 in the function of omega. This is called the frequency response. It will be zeta I divided by h mu dq. This is if the omega is 0, everything stops here. Then you don't have the following term. But now omega is not 0. So you have a very huge term followed. And some geniuses know how to further simplify the whole equation by letting a parameter, let the BGA NP0 divided by tau p. We call it the resonant frequency. So this is a term for the simplification, but it is also important because after you replace that, the frequency response will be the first is the static term, the steady state term times 1 minus omega divided by omega squared plus the term with the phase. Because this is a real number, this one is I, so that means the response of the photon and the current might have a phase delay due to the interacting time. It's still finite, although it's very, very, very small, but it is not 0. So you might have a phase delay to describe why it has an imaginary number here. Okay, so let's see how it should look like. For the first case, if we let omega to be 0 or to be nearly 0, that means you turn on and off quite slowly. And omega is much smaller than omega r. So the whole term becomes the original expression of the diode laser. So this is, we can call it DC limit. DC means, because we have another DC in the next page. This DC means the recurrent. Okay, the recurrent limit. Okay. And the second case, we let the injection current accelerate much faster than its response current, resonant frequency. Then omega is almost infinite, and the numerator become the denominator goes to infinity. So P1 over Pi0 goes to 0. That means no response. That means because you are increasing and reducing the carrier density too fast. It is too fast for the photon to catch up the change of the carrier variation. So the total output power is actually much smaller than its DC limit. Okay, so let's consider this is the blue one is the DC term. If you have a central and input power and the central output power here, while you are varying quite slowly, like here, it will give you a photon response with the same amplitude as DC. But if your input current is too fast, that means you're changing back and forth very, very, very fast. Then your output power response cannot catch up. Compared to the DC limit 0, if in the DC limit the amplification is 1. But because you are operating it too fast, the output power could actually have a much smaller variation. than you expect in the DC limit. Okay, so another the case is somewhere in the middle. It is omega close to omega r. The denominator is reaching its minimum value, and the P over I will be its DC response times something larger than 1. That means the carrier injection, the escalation match its peak of the optical modulation. So, although you are still modulating with such region, but your optical power is actually escalating higher than its response. So, if we really try to control the frequency response, we can define that one is the P over I is a specific omega, normalized to the response under DC limit. So we can normalize the first term, the zeta D over H mu over Q. We are only, this becomes a uniless value, which is equal to the second term here. What this should look like. So, the figure here, this is the frequency response. This is the y-axis is the modulation frequency of your current. Y-axis is your the optical signal modulation compared to DC. So while the frequency is really slow, the frequency response is 1. This is the limit. So we usually like to plot this with a decibel, 分贝 DC dB scale. dB scale means you times this with the log. Log with under log was a 10. Then times 20. Alright. So now we care a value called 3 dB frequency. What does 3 dB mean? 3 dB because 3 dB is the value of log half. Minus 3 dB is close to 20 log. And the log with a base of 10. If it's not base of E, is base of 10 times 0.5. Okay. So when the frequency is in the middle, while it's even closer to its resonant frequency, it increases first. Then as the frequency goes slightly, eventually cannot change that. So it will go up first, then it goes down. And we pretty care what's the frequency. It will intersect the number of 3 dB. When the frequency is under the number of 3 dB, that means the modulation, the scale of the modulation will be only half of your original steady state signal. Alright. So the 3 dB in angular frequency, if we want to know in the time frequency, we need to divide it into pi. And it should be something close to 1.55 divided by 2 pi times omega r. And the omega r can be written as 1.55 gamma VGA if you simply do assume this to be 0.05 or 1/2. Then put omega to one side and to the other side. So I already tell you what the reason is. You don't need to do that by yourself. It should be gamma GA divided by H mu divided by VA times zeta I divided by zeta D, and there's a square root here. Okay, but this is not good enough yet because there's something we don't know. But we don't what's the problem? D A H mean gamma B G A. Almost everything is the same. Okay, yeah. We only replace the zeta I to zeta D into a term like this. Okay. Why does a 3 dB frequency important? Because while we are sending signals for telecommunication, we are actually sending signal with 0 and 1. And then sometimes or most of the times something will give you a sequence of zeros. So when it has a long 0 or long 1, it will be the case like the steady term. But while the signal with alternating 1 and 0 very fast, it will be approaching its high speed term. So while we are calculating, or the machine is trying to okay, this is the axis is time, and it might reaching a signal like this. Okay, so it's pretty complicated. So because it has high low, so it will find its maximum value called 1, and its minimum value called 0. And because the signal might be always reach 1, or sometimes it will even surpass. So what it will do, it will detect if the signal is larger than 0.5, it is read as 1. If the signal is weaker than half, then we count it as 0. So then we can further transfer the optical signal back to the electrical signal. If the signal, the speed is fast, so its amplitude is approaching the half of the original steady limit. That means you are starting to mix, or you cannot to tell what's the difference between 1 and 0. Then your data has a lot of error. So the 3 dB frequency give you the maximum operational bandwidth of your communication. We are always trying to find a laser with a higher resonant frequency, or because the 3 dB is directly relevant to your resonant frequency. If you have a higher resonant frequency, or you have a higher omega 3 dB, your signal can be transmitted with a wider bandwidth. So many data can be sent from one end to the other end in a limited end of time. So how to for a laser, if you want to increase your speed, you need to give a good F3 dB. Try to make the 3 dB as large as possible. So now what we can do. So we want to measure large F3 dB. So we can probably we can let the numerator large, 我们可以让分子高一点 or to let the denominator to be small. Both sides will do. So the first, if we see the confinement factor, we have a gamma here. So if your cavity has a stronger confinement factor, that means your photon has a higher probability to interact with the injected carrier. So surely the response time will faster. So you might consider to make a stronger confinement factor for your laser. Or we can try to increase the differential gain, aka the term A, since it's also in the numerator. In order to make a differential gain, that means you need to inject the same carrier but increase more gain. It will be achieved if the density of state was low. Yeah, if your density state is pretty high, it will be more difficult to separate the EFC and the EFB. So the differential gain will also be smaller. Maybe you can take a look back to your lecture 6. We can also try to make the efficient carrier injection excisions delta I higher, or we can also try to reduce the active volume VA, or we can also try to under higher injection current. That means we are trying to shift the equilibrium precision from lower lacing to higher level. If we simply read the final expression of P0, it should be pretty effective. But I leave a question mark here. Because if the output power is too high, you have heat dissipation issue. The IV curve not necessarily leave a straight line here. This is the output power. This is the current. And ideally will increase like this. However, in reality, it will be something like this. If now you are operating under such a region, it not necessarily give you a wider response of your photon energy. So, generally speaking, we are trying to increase the output power of the telecommunication communication as much as possible, as long as the heat management is well controlled. So now we can consider two kinds of two lasers we commonly see. One is edge emitting laser. One is VSO. So while we are trying to make a telecommunication laser, which might be a better candidate. So for a VSO compared to ES, it has a shorter cavity. And it has a mirror with almost the unit at both sides. So confining factor probably, but it is difficult to say because you can also make a good design to make the confining factor in ELS to be high as well. Differential gain, this is more about the material you used. So probably not relevant to your cavity, to your cavity design. Injection, you're probably the data level. So the issue is small active volume. Since the VSO is only few micron in radius and only few nanometer in half. So because it's a pretty small size of the device, because of the much smaller device active region than ELS. So surely the intensity is not a problem. That your emitting side and the transmission side is close enough. A VSO will be a better choice for your communication. The ELS, because the wavelength is few hundred micron long, so naturally you will have a much larger active volume than the VSO. So for a short distance, rack-to-rack communication is always VSO. Few people really try to use the edge emitting lasers. But however, for very, very, very long distance communication, like a signal from Taipei to New York, you need to go really long distance. It goes back to the edge emitting laser, but that's not because it needs a higher power. It's because the edge emitting laser can have a more design to control its lasing wavelengths. So that will be also the topic in the future.